So my name is Raymond Law, and I work for Lowe's. I think the first thing to say is I am not an optical guy. I'm here to talk electrical and copper. And I hope to convince you that for very good reason, we start here. So very quickly, I have too much material, so some of the slides is going to be a little bit quick. So the company is Lowe's, and we have a booth, C9. Please come by and check us out. And my contact is right underneath the company information. And personally, I'm a EE electrical engineer, and my specialty is in signal integrity. Okay. So moving on, just a little bit of the agenda. So I'm going to start with the scale-up network. It's a very good place to start, just set the stage. And with that, I want to show some of the information about the length requirement. And that's why copper is still important. And then the backplane topology, we'll look at the connector, the cable. I'll touch on the co-packaged copper, which is CPC, and the near packaged copper, which is NPC. And of course, I'll also touch on just a little bit about the active component, which is repeaters. Then I'll move on to talk about the front panel pluggable topologies. So with that, that should round up most of the topology you'll see. And then we'll go into where copper may end and optics is going to take over. And I'll close the talk with some of the other high-speed interconnect needs, and of course, a call to action. Okay, let's start with this. I'm quite sure at least most of you have seen these two block diagrams before, so I'm not going to go into a lot of detail. But the important things that I want to be like a takeaway is, if you look at your left-hand side, the scale-up network, the purple area, and on the right-hand side, the UA-Link, what I would call a physical architecture, right? That gives you the high-level idea of what the network and the connection may look like. And I circle something out. Those are the things that I want to point to. So for scale-up, we need high bandwidth, low latency, accelerator to accelerator connection. The purpose is to, from the outside, you want the whole part or the node looks like one big accelerator with all the memories there. So that's the purpose, right? So it cannot be too far away. So right now we are talking about, well, for the slide it say 1 meter, probably going to be longer than 1 meter, and I'll show you why. And the data rate right now is, for 200G, we're talking about 200G, is the 802.3 DJ 212.5 gigabit per second, to be precise. Okay, so here I borrow a couple block diagrams from the OCP PCIe Extended Connectivity Requirements white paper. Of course, you cannot read all the detail, and you don't need to. It's just showing you what the cable management may look like if you want to wire within the rack and from rack to rack. And one thing that is very obvious is the author of the white paper assumed that your cable need to go to track or you need to go to ceiling. That makes the cable really, really long. And I would like to, at the end, call for action is find a way to don't do that, or else you are going to really waste a lot of resource. But again, highlighted here, if we are doing within rack, let's say you do 1 hop, and it's going to be maybe 1 to 2 meters, depending on do you need to go from the top to the middle, or from the top all the way down to the bottom. 2 meters should be enough maximum. If you go from one rack to the adjacent rack, again, depending on how you do it, a really rough estimate, 1.5 meter, maybe 2 meters. Now, if I just do a back of the envelope, if I want to go 4 rack out, 4 times 1.75, 7 meters. So we are talking about a scale up that maybe within 10 meters, hopefully no more than that, right, for 200G. Okay. So something to just keep in mind. So now here, backplane with in-rack connectivities. So on the upper left-hand corner, a very simple block diagram, what it looks like. So let's say it's from a GPU going down to a switch ASIC. Just an example, right? So you have the board trays, you have the backplane connector, and right below the block diagram is actually NVIDIA, I believe it's NVL72. You can just find it on the internet. So that's how it looked like. And IEEE, they are very kind, they very kindly put many things in the public domain already. So these, again, you can just download it from the internet. You don't need to sign up or anything. So that's one of the study they have done. Again, high-level takeaway. In the middle, cable assembly, 1 meter, completely passive. There's no active component. And the loss budget cable assembly there, 16.3 dB. So work already done for us. 1 meter cable, no problem. So with 1 meter backplane, you can already reach half the rack with in-rack. And there's no secret sauce, anything, right? So if I move on just a little bit, so here, sorry. Just a little example of what a backplane connector may look like. So this one, we actually have sampled in our booth. So if you are curious, come by C9, you can take a look, play with it. And on the right-hand side, just some example of the coaxial cable at different frequency, what the loss look like. So previous slide I showed you, right? The cable assembly, roughly 16 dB. Over here, you just do a really back of the envelope, just do a arithmetic. No issue, we can do that today, okay? Now, if you need to go all the way from top to bottom within the rack, 1 meter not enough. We need maybe 2 meter, or at least 1.5 meter. So one trick to pull is to use CPC or MPC. The block diagram is very, very simple. If you, again, come by our booth, we have CPC sample that you can take a look, play with it. There's some more details there. But suffice it to say, if you can mount the connector near your ASIC, the GPU, the switch, doesn't matter, either CPC right on top of the package or near the package, you can use internal flyover cable there. And that will give you extra loss budget to make your external cable or the backplane cable longer. Here is the example. Again, IEEE already done the work. Some nice people already work it out. When you have the time, maybe later on, look at the slide in detail. The bottom of the table there, I believe it's 1.4 meter. The cable is 1.4 meter. And they actually still leave behind 2 inch on each side for the motherboard. So this is something that we can do today. Within one rack, copper can handle 200G, more or less. And just some example of the MPC and CPC connector here. Moving on. Backplane with repeaters. So if 1.4 meter external cable is still not enough, long enough for you, one final trick, flow in an active component. Actually, it's nothing too groundbreaking. PCIe has been doing this for a long time. And by repeaters, I mean redriver, usually linear redriver, or retimer. And over here, the block diagram only show a board trace going over to the active component. But in reality, nothing stops you from using MPC or CPC to fly over to the repeater if the implementation requires it, okay? Right, so, but with active components come complexity. Retimer is easier to implement because it retime, but you pay higher cost in terms of dollar, power. For redriver, it's a little bit cheaper, and usually you don't need a heatsink. However, tuning of the redriver takes some time and takes some specialty. So that's your trade-off. Okay, so move on to front panel. Front panel, actually, I believe a lot of people here from the optical background, you know front panel maybe even better than I do. But the example here, I just picked an OSFP example. Again, standard, straight out from IEEE, 1 meter cable in the middle, and with, I believe it's, the author didn't write down how many inches of the motherboard trace. But again, it's already done. Analysis is out there. Nothing particularly troublesome. Something we can do. And on the right-hand side of the slide, just an example of our OSFP cage with some of the information and the insertion loss and the return loss profile. Simple stuff. Okay, all right. But 1 meter cable, does it really bring you what you need? Of course not. If you need to go from rack to rack, we're talking about, what, somewhere 1.5, 2. If you want to go more than one rack, a few meters. So one thing to do to extend that length is to use the repeater. And with a pluggable, you can actually put your active component on the pedal card that go into the plug. With that, one of the examples that I highlight, 224G ACC. ACC is the active, which is the redriver copper cable. And we can do 2 meters. Also, today. It's nothing particularly, how should I put it, troublesome to implement. It's already there. Okay. All right. So here is the lead in for all the other presenters after me. So you have been listening to a copper guy, but this is actually an optical workshop, right? So walking around, I hear people talk about optics all over the place. But exactly where do you want to switch from the electrical to the optics, right? Because coming out from any SoC is going to be electrical. You can put it using CPO, right, on the upper right-hand side, the CPO. You can just put it on top of it. But do you really need to go there? Remember, as far as I know, everybody I talked to so far, they still say that copper interconnect is cheaper, it's more reliable, and it burns less power. Optics is coming. I am not disagreeing with that. Actually, I wholeheartedly agree. However, you may want to pick the location to go from electrical to optics carefully, right? So there's the CPO. You can put your optical engine in your pluggable. Again, today this is happening. Or you can use NPO. You can use NPO and you can fly over and go to your front panel optical connector. All of these are options. And I am sure all the presenters after me, they'll give you a lot more information than I can. Okay. Here is some of the other high-speed interconnect needs that I just want to showcase. Because it takes more than just a scale-up network to put a server together, right? So from the upper left-hand corner going clockwise, we have the 224G card edge cable connector. We have like a NPC, but it's belly to belly. So depending on your topology, you can actually, on top of the motherboard, you can have one connector, right below it, you can have another one. Pretty convenient, actually, think about it. And of course, we have PCIe connector. This is a CAM connector. But the good thing is, the MCIO cable direct attached to it. You don't need to have baud route. Baud route is high loss. If you want to route longer, MCIO near the package, fly over, right there. And of course, memory. I don't need to talk much about memory. Everybody say they need more, they want higher speed, all the whole 9 yards. And coming down, there's the orthogonal EDSFF. This one is Gen 6. But right next to it, Gen C, we have Gen 7, PCIe Gen 7 data rate. And then to the far lower left-hand corner, the MCIO Gen 7. Okay, so this is some of the things that round up the what I want to show here. But I do want to spend a couple more minutes here on this call to action. Again, you are listening to a copper guy in an optical workshop. So the one thing that I want to really highlight in the past few minutes is I want to convince you at 200G, copper interconnect can still play a very significant role. It's not that, far from that. And again, it's still more reliable, less power hungry, and costs a little bit less. And if you are going up and down the rack, it can potentially be all copper. If you just go one rack over, maybe even up to 2 racks, it depends on the implementation. A lot of it can be copper. You may need a repeater. Now, but when are we going to when will optics take over? I keep thinking about this question in my mind. I want to keep my job, being a copper guy, right? But I have to deal with the optics coming. Where is optics coming? So the call to action from my side is, I think we need to have a more holistic system approach in designing the scale up. I cannot say that copper will run forever, that's obvious. But I also find that, all optics, that is also unrealistic. So we want a more holistic view. Where to begin, where to end. What is the latency requirement? That is one of the important questions that will determine how long you need to route. If you only can do 1 hop, okay, that's pretty short. But if you can handle 2 hops, I am not a network architect, so I don't know all the trade-off. But if you can handle 2 hops, why not? You can still make a scale-up network, implement it, and with the proper length requirement in your calculation, things can be more affordable and it's more reliable with copper. Okay, so from OCP perspective, maybe we can have some guidance on the physical architecture of the interconnect, right? And cable management, one of the earlier slides. You make the assumption that your cable need to go up and down the track or fly through the ceiling. Oh my God, do you really want to go there? So, but without those tracks, how are you going to manage all the cable? They are heavy. So how are we going to do that? So this is, I don't have an answer, but hopefully as a community, we can come up with something. And the final one, the usage guidance on active component is not obvious. Retimer is easier, but it's expensive. Redriver is harder. If there's some kind of guidance that can help with that, it would be great. With that, I think I am out of time. Thank you very much.